Everyone is back. Who is not? I need to perform a readiness check on this raid, so it's better to ask who is back here.
I am here.
Okay, almost everyone is back here, which is good enough for me. So I'm going to proceed, and this definition of H length does not assume anything about its elements, but some other definition, let's say a definition like sum, would need to. So in order to sum all of the elements of a heterogeneous list, we first need to define a way to convert a single element to a unifying representation, because our H sum is going to have a type like this: sum constraint, then H list of x's, and then rational, because any number that we care about can be represented as a rational number. I hope. Uh, because we are using computers with finite memory, and anything that is not rational is not representable anyway. So I'm going to write some constraint here, like I did with another definition of sum, which was using sum. My pronunciation becomes very confusing at this point. I mean, uh, this, let me scroll enough. This definition, which I'm going to post here. So this definition of maybes of real numbers, it was using two rational, and that's what we want to do here as well. We want to write H sum, which when given nil will result in 0, and when given ons will use two rational to convert the element, and then sum the rest of the elements. But of course, we need a constraint like real to put onto every possible every type that is contained in this access list. And how could we do that? Well, the way we should do that is using type families, also known as give me a moment, also known as type functions. Functions, because they are type functions, they take types as input and they give you types as output. So when we write a regular function that has that operates in terms, it has a type signature, and when we are writing type functions that manipulate types, we are going to write a kind signature for it. So I'm going to use some pseudo-Haskell, it's not real Haskell syntax, to explain the concept, and then I'm going to rewrite it with actual, horrible, ugly Haskell syntax that I hate. So let's get started. We are going to write a function on types called allConstraint, and here is its kind signature. It will take a constraint on a single type, and it will give us a constraint applied applied to a list of types. So all constraint f of an empty list of types is a unit constraint. This constraint is always satisfied. So if you write x unit constraint to int, you can just write 5 because this constraint, this unit constraint, there's nothing needed to satisfy it. The GHC will just supply the dictionary which contains nothing. It's like unit type, but unit constraint, no information content in it. And all constraint f for list types, of course, is a pair of constraints. It's f of x and all constraint f of x's. So this is how we would define the all constraint function on types if Haskell had sensible syntax for type functions. And here's how we would use it. We could say foo all constrained EQ ABC, and this would be equivalent to EQA, EQB, EQC. Like this, it's just a function. You give it its inputs, it reduces, and it gets, and it produces an output. But actually, this here will be structured like this. It follows from definition, but conceptually, it is equivalent to a big flat constraint. Just like with tuples, we can have nested tuples, and we can have flat tuples. So if this was a real Haskell, I would not be able to write a function on types at all. I would be writing a type family, which is Haskell's jargon for type function. This is type family, all constrained. It's taking some f with kind type to constraint. It's taking some x's with kind a list of types and gives you a constraint, and it already doesn't fit. Well, too bad. I'm going to erase parts of this. So GHC will infer it, so it will write. Now I'm going to define two type instances inside this type family. I'm going to write all constrained f prime empty list equals unit constraint and all constrained fx x's equals fx all constrained fx's, like this. So this is what we write in Haskell, but of course conceptually it's just a function, nothing fancy. And when we define our hsum, which I'm going to copy, then the constraint we put to the left of the big arrow is all constrained real access, and this will work. But I want to explain in detail why this is going to work, because it's not as intuitive as you might think, because this access, this list of type parameters, it could be potentially infinite, meaning that this type family, it wouldn't, it doesn't work like this. It doesn't work like this type family first reduces to a big constraint and then our function starts to work. They work together in lockstep. At each iteration, the type family reduces a little bit and the function reduces a little bit. So in this clause, nothing interesting again. But here, I'm going to rename access to A's here to make a presentation a bit less confusing due to reusing names. So what's going on here is that when we pattern match on the cons constructor, the first thing we learn, all right, I'm going to rename it again Q and Qs, but the constructor has type like this. So in addition to Q of type A and Qs of type H list of A's, I get an invisible input to this function, an invisible value stored in this hsum, in this cons value constructor. This is the equality constraint stored in it. This equality constraint tells me that the access, the same access that we have here and here, does Google Docs display what I select with my mouse? Because I was relying on that heavily. All right, so this access in the equality constraint, the same as here and here. We now know that it is a non-empty list. It is A cons A's. What this means is that the all constraint type family can reduce. It can reduce into this. So this clause of the type family gives us its right-hand side, and since we know that access is A cons A's, this is FA, FA's. This is what we are working with now. And since we know that F is real, it's real here. This is the context for the right-hand side of this definition. And what we are calling here is to rational A. This relies, to rational Q. This relies on the real A constraint, because otherwise we would not know how to call to rational. So this needs real A. And the second part, H sum Qs, it needs all constraint real A's. Why does it need that? Because we require it in type signature here. We say that to call hsum, you need to know that each element in the list is real, and here is what we have. We have a proof of that. But we only have a proof of that because pattern matching on cons allowed the type family to reduce. If we did not pattern match on cons here, the access list would remain opaque and the type family would not reduce and we wouldn't be able to do anything with it. So an alternative which would not work is that if we tried to do something like this, if we said, okay, so let's take h head, it will give us, it will take list of x's, and it will give us some element x, which we will compute using partial type family head. Like this. So this is head of x's h head. It's maybe, of course, because we don't always have a head. H head of nil is nothing. H head of a cons something is just a. And this definition will work, but if we try to define the second clause of h sum like this, so this is just queues. I'm not pattern matching on the cons constructor, and I'm trying to case h head queues of nothing. Impossible. It's impossible because we have a previous clause in hsum which says that we already handle nil. So impossible due to hsum nil clause. But the just clause will give us q. And what if we tried to call to rational q plus blah 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 something here? Let's say I'd also define h tail, but I want because this will already break this here underlined will not work because here the all constrained real type family does not have a proof that queues is a non-empty list. It cannot reduce to its constituents real A and all constrained real A's. So in order to use type families like this, we need to drive their reduction with pattern matching on term level. This will bring equality proofs stored implicitly inside JDT constructors, and those proofs will help JDT understand that our type variables are they have some finite set of possible values. What I mean by that is that you might have expected GHC to reason for you here. You might expect it to generate different code depending on access being an empty list or a non-empty list of types to adapt to those different situations. It will not. It will need your guidance. It will need you to bring the equality proofs into scope to work. And that's a good thing because you don't want GHC to generate pattern matching on types for you. It would first of all make dubious definitions like this possible. I better not get started with evil ID maybe another time, because we have other things to cover. Sum types. All right. Sum types. There is a very familiar sum type to everyone. It's called either A, B, and it's called a sum type, unsurprisingly, because the amount of elements of a sum type is the amount of elements of its first constituent plus the amount of elements of its second constituents. An example like before is that if we have either bool color code, we have 2 plus 3 equals 5 elements. It's left true, left false, right red, right blue, right green, total of 5. We have 2. We have a sum of the amounts of elements because we either have the elements from the first type or from the second type. So it's a sum of possibilities. I don't know how to explain it other than saying that it should be intuitive, but I know that for some people it's not intuitive. So sorry for that. I'm just going to move on and say that similarly to how we have a product of 0 types, which is unit, and unit multiplied by A is A, we have a similar type, which is a neutral element for either. So from our experience with numbers, if I add 0 to A, it's A. If I add A to 0, it's A. And with types, if I have some type with 0 elements, so no elements possible for this type. This is somewhat hard to grasp because I have been trying to explain this concept to very smart people and they still struggle, so don't worry if you don't understand it, but it's possible to have a type with no elements, meaning you cannot construct it and you cannot pattern match on it. This data type is void, and one second. This data type is void, and there is this is the entire definition. So this is it. This is the empty type. There are no constructors to define for it, and when you have, and what you can define for it is a function called absurd. You say that given void, I can give you anything. And the way to write this function like this, I'm going to take value of type void, which is already absurd. There can be no values of type void, but I'm going to pretend. So let's say I have a value of type void. Let's say the impossible happened. Let's consider each value of void on case-by-case basis, because you see when you define a function, you normally define it on case-by-case basis. You define not from bool to bool, not B, case B off, case true, I return false, case false, I return true. Case by case. And here I'm going to do exactly the same. I'm going to say consider each possible value of void, of which there are none. And that's it. So these curly braces are regular Haskell syntax. I can have written the pattern matching in Node like this. Just using these semicolons instead of indentation, and the same is happening here. I have an empty sequence of pattern matching clauses because there are no values to consider. So if you ever see an invocation of absurd in code, this means that this code will never be called at runtime. It is something that we just call so that the compiler will realize that we are dealing with something impossible. And this requires the empty case extension, which before GC 8.2, I think, was utterly broken. But now it's not. Hooray! Now let's move on to some types which have void as their neutral element. So either void or A is the same thing approximately as A, and either A void is the same thing approximately as A. Why? Because you can convert in one direction. Here, let's say I can convert from A to either void A like this. It's just right, and two. And I can convert from either void A to A like this. From is either absurd or identity. So either is a combinator from base, which does pattern matching for me. It's just for conciseness. And the same argument applies to void in the right component of either rather than the left component. Similarly to tuples, we could define flat sum types for any length. So I could define either 3, so it wouldn't be left, right, and middle. I'm just going to adopt a boring notation instead. I'll call this element 1 of 3. A, element 2 of 3b, or element 3 of 3c, and similarly for the sum of 4 types, A, B, C, D, 4, 4, 4, 4. But why would we repeat the mistakes of tuples and do this when we can just move on to defining sums like we did H-lists inductively? I'm going to skip the derivation where I used a list-like structure for tuples before H-lists. So we could just as an example, I'm going to write one type signature. So either A, either B, either C void, which is similar to a list in the sense that we have cons, 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 nil, where void serves the function of nil, and either serves the function of cons. But it's a different type at runtime in the sense that it's only a value of one of those types, not a value of each of those types. So possible values here are left A, right, left, B, right, left, C of type C, and there is no possible value for void. We cannot construct it. It has no elements. So that's it. A sum of 3 types. And we can define this using JDTs. We can, instead of an H list, define H something, H union, let's say H union, or actually I will call it open union. It's a common name for this type, which will take a list of types and give you another type using some of its constructors. So the first definition I'm going to give, I'm going to try to make it as similar to HLists as possible, so that you can see the parallel between those definitions. The HLists, we define them like this, but we also could have defined them like this. So here we have a unit, and here we have tuple. So nil is like base case. It contains the neutral element, and cons is like the induction case. It contains the tensor operator, which we use to combine the head of the H list and its tail. And with open union, we are going to have something kind of similar. We are going to have open union nil, which will contain void instead of unit, because void is the neutral element for a sum. So here is our nil, and open union cons is going to have the same constraint that the list is non-empty. And then it will use, rather than a tuple, it will use either to combine the elements, either a open union A's. This will give us an open union of X's. So what I did is I took the definition of HList, I replaced a neutral element for products by a neutral elements for sums, and I replaced products by sums. And that's how we get an open union by a mechanical transformation. But then we can notice something. First is that the first constructor is entirely redundant in that it cannot be used. You cannot give it void to construct it. So, and when you pattern match on it, the only thing you can do is call absurd on this void. So all it gives us is boilerplate. So we can, in our next iteration of open union, just remove that structure. We are losing nothing by doing so. And in the cons constructor, we can sort of decompose it into two, like this. So I'm going to copy this constructor and say that here in the first one, I'm going to only store the thing on the left, And in the second one, I am going to store only the thing on the right. And I get basically an equivalent definition because earlier I had cons containing left and cons containing right, and now I just have my own left and my own right. So it's equivalent. And the names I like to use for this constructor is not left and right, it's this and that. The reason that I like those names is how terms look. So for instance, let's say I have an open union of types int, char, bool. What are possible values of this type? First of all, we have int, and this is the first element in this list of types. So if we look at the constructors available for our use, this and that, if we want to use int, if we want to store int, we are going to use the constructor called this, as it contains the head of the list. And this will be, for instance, this 5 or this -3. If, however, we want another type from this list, we can say, don't use this type, don't use this first type, use that other type from the tail of the list. And here, what we now are trying to construct is an open union of either char or bool. This now means that we get the same choice. We can use the head of this list char or proceed and go to bool. So I'm going to use the head here. I'm going to write this and use a char x. It will work. But another time I would say don't use int, use that other type. And inside of here I'm saying don't use char, use that other type. That again. And finally, I have only one type to choose from, and I have to use this. This true. That's how an open union works. It's like an either in types. So HList is a tuple of many types, and open union is an either of many types. And when you have an open union of an empty list, you can convert it to anything, because it is, of course, impossible to have such union. So this pattern matching, it will have an empty list of clauses, because if we try to pattern match on this here, GHC will derive a contradiction. It will see that we have a proof that access is a non-empty list, but here we say that it's empty. It's nonsense. GC will reject it. And if we try to use that, and the same thing, it says that access is a non-empty list, and yet we say it is empty. It will say nonsense and reject our program. And the only option we have here is to use an empty case match. So in this sense, we have retained this phantom void value in our definition, because we still have that the union of an empty list of types is absurd. It has no possible values. And the relation between tuples and HList is that of the multiplication operator and the product function. All right, so this is like the tuple. This is like the H list. And the same argument can be made for open union. So either is like the plus function, and open union is like the sum function. So are there any questions about sum types? All right, so if that is clear, I am going to move on to the next topic. This topic is data families. So data families are like it's sort of a hybrid between type families and data declarations. So they are similar to type families in the sense that they are two type functions. They are a sort of type function, but they are similar to data declarations is that unlike type families that are reduced to existing types, data families declare new data types. So I can have a type family F which takes some boolean B and gives me a type, and I'll say F true is int and F false is char. And I can have this used like this. So f of true to int, it's id, and g f of false to char is id as well. So what's going on here in this contrived example is that f of true as a type function reduces to type int. We have int to int, and that's one possible definition for such a function is identity. And f of false reduces to char, and we have char to char, and that can be identity as well. So type families, they being type functions, take types as input, give you types as output, but data families, they are like data declarations, because instead of giving you existing types as output, they create new types as their output. So if I had a data family, okay, so an example in the chat, in the Slack chat, is how is this different from dependent types? My question is, how is this similar to dependent types? Because we don't have here types depending on values. There is nothing here that would, so we don't have something like this. We don't have a function f that would take some boolean and give you f of this b, because this isn't even valid Haskell. I'm going to use single colon here to demonstrate, because this is, if I use double colon here, this would be a kind annotation, but this here is not a kind annotation. This is me trying to refer to B, which f is going to take. So let's say f of B equals case B of, if I get true as input, I will return f of true, so an int 5, and if I get false as input, I will return f of B, that's char. But
well, you do have a type that takes a value that is a Boolean value as input, and it returns you a type. So you have a function from values to types. But the question is, how is this different from dependent types?
So what I'm showing here, f, it's a function that takes a Boolean as input, and this Boolean will be supplied at runtime. It's a regular term level function, and yet its type depends on this runtime value. We apply this f to B, but this is not valid Haskell. This is an example of dependent types, not Haskell. This is not valid Haskell. Why? Because we cannot refer to this term level B. So this B is the same as this B, and we cannot refer to this term level B on the type level. This is what dependent types are, and we don't have that in Haskell. We can call f on some existing type level values. We can apply f to true or f to false, but this is not dependent types, because those true and those false, they don't come from terms. They are not runtime values. They are not input to our term level functions. So basically, if you want to see a deeper connection between dependent types and what we are discussing here, I suggest you Google Lambda Cube. I'm going to share a link in the global chat. And in this Lambda Cube, you can see many type system for Lambda calculus, but what I'm going to draw your attention to, assuming you open the link, is that we have 4 possible forms of abstraction. When we have regular Lambda functions that take values and give you values as a result, that's just a basic feature of Lambda calculus. It's not even mentioned on the Wikipedia page, but we do have that sort of function. It takes a term and it gives you another term. That's how Lambda functions work. But then you can have values that depend on types. So you give it a type and it gives you a value. An example of this is type classes in Haskell. You give it, let's consider the monoid class, and in particular its method mempty. So when you say, I give you type some int, what is the neutral value? And mempty equals 0. And when you give it product int, you ask it for this type, what is the corresponding mempty term? It gives you 1, and for unit it gives you unit, and so on. So for list it gives you an empty list. So it takes a type as a type class, you instantiate it to a type, but you get a term for this type. Those are terms that depend on types. So we have 2 sorts of abstraction. Terms depending on terms, that's Lambda functions. Terms depending on types, that's classes. Now I have introduced types depending on types. that's type level functions, that's type families. But to have dependent types, we need a fourth kind of thing. It's types depending on terms, completing the cube with the fourth kind of dependency. We need to be able to take a term like this, b boolean, and compute a type based on this term. Here, false and true in F and G, it's not a term, it's a promoted constructor, and it's a type. And you can see that it's a type because here on the term level, not to the right of the double colon, but to the right of the equality sign in the definition, you cannot refer to those things. But in dependent types, there is really no distinction between a variable bound to the right of the double colon and a variable bound on the term level to the left of the equality sign. So basically, I can say how this is different from dependent types because it's just a different sort of abstraction. Dependent types are types depending on terms, and here we have types depending on types. Classes are terms depending on types, and regular lambda functions are terms depending on terms. Does that answer your question?
In fact, the question was about the values true and false being promoted. So you said that they were, and it was not completely clear from the code. If they were not, I guess it would be a good idea to assume that they were actually representing dependent types.
Okay, so the data kind extension that we covered before, it just enriches the grammar of kinds, and these true and these false, I can write them with a prime. GHC will accept that, and this should clarify that those true and false are not related to term level true and false in any way. They are just in some sense copy-pasted internally in GHC. So GHC does not see connection between this true and a term level true. This is a type. It has kind bool. So this is type. This is kind. But in a function like not, we take b of type bool. This is a term. This is a type. So let's say this is pattern matching on true. So let's move on. This is true. Unrelated. This is unfortunately not Haskell yet. We are going to get there sooner or later. I'm going to play a role in this, I hope. So data families, they are like type families. Even the syntax is the same, but then we are going to define data instances for it. So data instance f of true is going to be, it cannot be an existing type, so we cannot write int like we wrote with the type family case. It must be something like to the right of a data declaration. So when we write a data declaration to the to the right of the equality sign, we start listing constructors. And here we are going to start listing constructors as well, rather than resulting types. So I will write make f true. That's the constructor name. And it will contain, let's say, 2 integers. And that's it. That's a data instance, which is like data declaration, but we get to this data instance by reducing a type level function. So the reason we might want to prefer a data family to a type family, so you might ask, why don't you write something like f_true type? Then if our data family is going to also return for the false case pair of chars, I'm going to similarly define f false. So why don't I just take those 2 types here and define a type family f of b bool, which would reduce true to f true and false to f false. So it looks equivalent because here we have a data family with 2 data instances which declare new types, and here we declare 2 new types, and we have a type family which reduces to it. So the reason you might want to prefer a data family is that it's better for type inference. And see an example of that, recall our earlier simple definitions of f true of f and g, which were defined like this. Well, actually, let's consider a different example. Let's say we are going to take coming up with examples is difficult, but I'm going to try. So consider some function f, which is taking f as a type family of b, and all right, examples are difficult indeed. Okay, so type inference aside, I could come up with an example if I took more time, but if you want a formal reason for why type inference for data families is better, is that for data families, when we have some data family D applied to type A, and we know that it's equivalent to some other data family G applied to type B. From this, we can derive that D equals G and A equals B. This rule holds for data families, but not type families, and GHT uses it during type inference. But that aside, the more important reason why you might want to use a data family is that, I think I have actually come up with an example of where a data family would be useful. So let's say I'm defining a value. Oh, never mind. So for another reason why data families are more useful is that we can partially apply them on type level. So I'm going to use this fact when I'm going to parameterize HList and open unions by an interpretation. So let's first try to define some interpretation. We already have one. It's F above. This interprets a Boolean as a type. So let's say, let's assume I have a type level map for lists, and I map F to list of true, false, false, true. This should give me, this should reduce to int char true, right? Because we are applying a function to each element of the list, just like with the term level list map, but it will not work. This could not possibly ever work for type families, because if we defined map, so it takes F axis and map F, map F. Just mirroring the map definition for term level lists. So this map will not. Did you mean int char int? Of course, yes. Sorry. So this definition of map will not work with type family, because type families, due to a completely artificial restriction in GHC, cannot be partially applied. So here we use F without applying it to anything directly. So we don't have F true, F false. This is called a saturated call. Saturated because we have provided all inputs to it. So F has one input, and we have provided exactly one input here. But in the map example, this is saturated, partially applied, and we cannot do that with type families. The reason that we cannot do that is that GHC relies pretty heavily on this assumption that I wrote above for type inference, and type families don't obey this law. They are general type level functions. They don't have to obey this law. So there are two options here. Either GHC stops assuming that, and it will wreak havoc on type inference, or GHC keeps assuming that, then type families are illegal. They are not types. So the way GHC solves it is that it makes type families illegal in the phase where it applies this assumption, but they are legal before it applies this assumption, but they must reduce before the time. So if you write f true, it reduces to int, and it's a valid type. If I write f false, it reduces to char, and it's a valid type. But if I write simply f, then it cannot reduce to anything as it hasn't received any inputs. So it's not a type. It's not something that GHC can even mention or talk about. So here, when I'm trying to use f as an input to map, it will fail because f is not a thing that GHC understands. GHC understands f true, f false, it can reduce those, but it does not understand f on its own. Because in order to understand it, it needs to learn that there are types that follow this rule, this assumption, and types that don't follow this rule. And at this moment, GHC does not make this distinction. So with data families, if I define data family F, I'll actually rename it to G. It does not work with type families. But if I define a data family, then this will work. This will be G of true, G of false, G of false, G of true. This is this will reduce nicely. This will work, and GC will accept it. So the reason I tend to use data families is that they can be used partially applied. There is a workaround for type families that after defining a type family, you define a new type around it, and the new type is can be partially applied as well. But the reason I still prefer data families is that they actually do have better type inference. So despite me saying earlier that I cannot come up with an example where data families can be beneficial for type inference, it's that I cannot come up with a simple example. I can show you the code, the actual code where it helps, but it will be not helpful because it's complicated code. But in complicated code, it is sometimes helpful. So moving on to our last topic, parameterization of H-lists and unions by an interpretation. This is basically the part where we get to vinyl or vinyl or whatever. Someone please suggest the correct pronunciation.
Vinyl.
Vinyl. All right. So vinyl and union. They are H-lists and open unions parameterized by an interpretation, which can be a data family or a data or a type constructor like maybe. It cannot be a type family, unfortunately, although it would be very convenient. So let's take the definition from vinyl and take it apart. I'm going to copy it from the library code and explain what's going on there. So here's the library definition. And the first thing I'm going to do is I'm going to remove those bangs because they are not important for the things we are discussing today. They help with performance of the library. Those are strictness annotations, bang annotations, which help GHC optimize the codes. Sometimes use a more compact runtime representation and reduce more eagerly, but for our theoretical presentation of this topic, it's not important. So I've just removed them. Then the kind signature of rec can be rewritten with named parameters like this. So we have some interpretation of this kind, and we have some elements of this kind. So this is for comparison, data HList is approximately the same thing, but without the interpretation. And we have two constructors, our nil, which is like nil of our HList, but it also mentions the interpretation f, and our cons constructor is very much like that of the HList, but it's written in a more concise JDT style. And it is parameterized by an interpretation. So if I get rid of the JDT syntax used here, the way it desugars is that we have a record access, but we know we have a proof stored here, a proof that says that access equals r cons rs. And here this is access as well, and we have a proof stored that access are equal to an empty type file list. And this, after undertaking some torturing, this definition should be understandable. It's like the HList we defined before, but parameterized by some f, and this f wraps each element. For instance, I can have an h. A question. All right, so prime colon to colon, the same as prime square brackets to square brackets, correct? The prime is a namespace resolution marker, which helps GHC distinguish promoted things and unpromoted things. But actually, in case of the list colon, it is optional, so I can remove it because there is no ambiguity. There is no type level thing named colon, so there is no need for disambiguation. Both are accepted. You can write the prime or you can omit it. So let's say I have a record where everything is wrapped in the ID new type, which is like this. So this record is boring in the sense that it is the same as an HList. So I can have, if this list of types is int bool int, I can have a rec of this type id 5, id true, id -3 are nil. And if I pick a different interpretation, I can get different results. That's where it gets interesting. So, for instance, if I don't care about the actual values, I only need to know the length of this type level list. I just want to represent its spine, its list structure. I can use proxy, which is defined like this: data proxy A is proxy. It contains no fields, it contains no value, so I can have proxy nil. Nothing useful stored on the term level except the length. We know that we have 1, 2, 3, 3 elements. That's what we know on term level. But we have the same type level list, and we can use more interesting interpretations like our data family G. So I can write, let me scroll up to see how G is defined. Okay, so I'm going to copy instances for it here. Name it to G. So G is a data family that will take a Boolean and give you a type, meaning that a record parameterized by G will actually have a type level list of Booleans which will serve as input to this G. So an example would be true, false, true. And then a term of this record will be G of true contains two integers. You can G true 1, 2, and make G false x, y, and then make G true -2, 7, and then are nil, and that's it. So the vinyl records are different from HList only in that they allow you to easily apply a type constructor to each element stored inside of this list. And this can be used for writing code that operates on the level of these interpretations, not on the level of individual values. What I mean by that is that if we define a type synonym for a transformation between interpretations, we can write code that will take a transformation between interpretation and lift it to a transformation between two records, like this. So AirMap is going to take a transformation T, then either R nil, then it returns R nil, or it's going to take fx's and give you tfx tfx's. So this mirrors the type what is it? The type signature of the term level definition of map, but it uses transformations between interpretations, and it gives you transformation between those records. The definition is basically a copy of the list map, so it can be like A to B, lists of A to list of B, lists of A to list of B. You can actually write the code like this in Haskell if you didn't know. Instead of writing it's like this, you can write it like this. It's the same thing, the same type. So this should really highlight the similarity between those two definitions. And for clauses, we have map f empty list equal empty list, and map x equals fx of x. So this actually helps me correct the definition below. Example of how I could use this transformation, a very boring example, but working one nevertheless, is that I can take my record of IDs, this one. So it's an example of record, and I'm going to air map a transformation that will take an ID of something and give me just proxy, and this will give me this will apply this transformation to each element of the record and give me a record of proxies. As I said, it's boring, but it is a working example. Now, the next thing I'm going to cover probably is why those are called records. That's because initially Vinyl was designed to solve the record problem in Haskell, and the record problem is that Haskell does not have first-class records. So we can write a record definition like this. And write a function that will take this record and produce something. But we don't have first-class records. We cannot write something like this. Unfortunately, but Vinyl, it solves it. We can define an interpretation called our field, and a field is going to take so it's going to take a pair of key value, and to make a field you supply the value and get a field with this key, basically. So field key value, and key value equals key value promoted. It's a tuple. So we can now write G like this. It will take a record of fields. So this is like a first-class record, and the fields are going to be foo int promoted, and bar char. So this is it. This is how Vinyl tries to solve the record problem by using an interpretation for fields. But the interesting thing is that this is the least useful way to use Vinyl. I don't use it like that. The actual use of Vinyl is by using your own data families as interpretations. And now to the library union, I wrote it because I wanted the same thing, but for open unions, I wanted to parameterize them by an interpretation. So we take our definition of an open union that I'm going to copy. We take it and we turn it into a union parameterized by interpretation in a very simple manner. We add f's to everything. And there you have it. Vinyl and union. You can write code using it. For instance, you can, let's say, take a record. I'm going to write function foo. You will take a record and give you some value from it. You don't know which one. Maybe it will give you value by index. So of 0 of a is going to give you this value, and foo of n is going to skip this value and give you that, and like this. And that's basically it. This function will compile, it will work, and you can apply it to, let's say, foo3 record of rec example that will be rec example that we defined earlier. I'm going to copy it. Actually, it should be 2, and this will then reduce to 0, 1, 2. This will reduce to that ID, this ID -3 parentheses. For n-1, correct. n-1. So having this defined, we can now, the reason that I wanted to explain these things, those unions and records, is that I find use cases for them quite often. And the last time I used them was to develop an extensible command language for a project in Sirocco. This extensible command language was based on the OX language in CredaneSL. The OX language could be used to send commands to the blockchain, but now in this new project, we needed to use commands from different domains, not only for the blockchain, but also for the user interface of this program and for other components. So what I ended up with is that I had a type level list of components, component A, B, C, and the regular pipeline in a language interpreter is that it first gives you, it takes text, it gives you a list of tokens, and then it gives you a parse tree, and then you run an interpreter on this parse tree, you get a value, and then this value as an output to the user gets pre-printed back into text. But in this extensible language, I take text as input, then I get a token parameterized by components, then I get a parse tree parameterized by components, then I get a value parameterized by components, and then I get text as the result. And the way the tokens, for instance, are using those components is that I have a definition which I'm going to copy. If I find it. Okay, so here's the definition of token that I'm using. The definition will look better in monospace, right? So as you can see here, oh, that's bad, right? So as you can see here, I have some common tokens which are square brackets, parentheses, the equality sign, the semicolon, identifiers for variable names, and so on. But I also have a union of tokens which each component can define individually. So it's data family like this. And a component may define an instance for it, so it's going to look like this. Component token for the core component is defined like this. We define in the core component, we define literals for numbers, strings, and file paths. So here's the data instance taken right from the actual code of component tokens for the core component. And the tokenizer, which is going to produce these values, is defined on per component level like this. All right, that's too much code already. Anyway, another thing I want to cover here before we end the lecture is how I'm using union to prove that some element exists in a record. So I mentioned that type REFL not without a reason, but because it's useful in conjunction with union. You can define type called lem proof of A's, which is a union of qualities between A and A's. meaning that if I have a type level list int bool char, I can prove that there is an int inside of it by using this raffle. This will have type lmproof int bool char, and I can prove that there is bool inside of it by using this raffle. This will have type lmproof bool char, and I can prove that there is char in it in a similar manner by using another that. So the way this works is that so Artyom asked earlier, why can't we use dict instead of raffle? I said because we want to use raffle, the equality type partially applied, and here we have exactly that. We apply it partially to this type A, and then we pass this partially applied equality to union, and union applies it to each element of the type level list. So this means that remember that union is like either it's one of the elements. So we have that either A equals to int for the type level list like this. Like this, we have that either A equals to int, or that A equals to bool, or A equals to char, meaning that A equals to something in this list, but not to anything else. We cannot have to string. That's impossible because we wouldn't have raffle for it. So that's a useful way to represent proofs that something, some type is in your type level list. And that's probably it. I don't think I can explain anything else without getting into specifics of the code for that language. But this would be probably better limited to developers of that are involved in this project. So I'm going to spend the next 15 minutes answering questions, and if there are any, and that's going to be it. Any questions? Is the last element of list an int? I'm not sure to what code snippet this refers to, because
Yeah, that
this
was
question
half an
was
hour ago.
asked, yes, half an hour ago, right? Can you elaborate on which problems Rec solves and how? So compared to H lists, with Rec I can now write code that changes interpretations. So, for example, this example with NEAT, with the extensible language, in this phase I have union of tokens, but on the next phase, I'm going to have a union of values during the evaluation phase, meaning that I have a function that takes union of component token components and gives me a union of component value components. You couldn't write something like that with an open union. And similarly for records, if you have some record f of access and you want to get a record G of the same access, the easiest way to do that, to change the representation, is to use the rec type, which already encodes the representation as part of its type. The alternative approach would be to use an H list and a type family like map, which I defined earlier, map f access. So this sort is equivalent to rec f access, but like this, is going to be way more annoying for the reason that I actually mentioned earlier, that type families, they have very bad type inference. So I'm not even sure that if I copy the definition of RMAP, that something that the equivalent definition will type check for this sort of H list, but I'm pretty sure that it works for Rex. So the RMAP definition, which I'm going to copy now, this works very well for records from vinyl, but it doesn't work at all. I think it won't work for H lists where you mapped in an interpretation to each element individually. So you want to use vinyl if you manipulate interpretations in your application. If you don't manipulate interpretations, if you have just a single interpretation identity, your code will be simpler with a regular H list. And if you don't need inductive reasoning, your code will be simpler with a flat tuple. So to sum it up, the problem that Rex solves is manipulating interpretations separately from the elements stored in those records. I meant I didn't get a trick with field. All right, so the trick with field is that all right, where is it? Here is it. So if you scroll 2 pages up where I define field, field is like an identity wrapper around a value, but it also contains a name for this value. So you can have make field containing 5, and this will have type field full int, for instance. You can give a different name, you can give it name bar or anything else. This here is a promoted pair, And when you apply this interpretation to a list of pairs, you get a record where each element is the second component. So this rec field fooint bar char at runtime will be this, will contain the same information. It won't be equivalent at runtime. You cannot unsafe coerce between those, but at runtime it will contain the a value of type int, a value of type char, and at compile time we also know the names for those fields, so we can write functions that, for instance, look up the field that we want and get its value for us. And that's what Vinyl actually does. If you look at its code, it's at its interface, you will find a definition called L-field, which is a thing similar to what I defined, and you will find you will also find in data vinyl lens, you will find a class called rec-lm, which allows you to get a lens into a field of a vinyl record using the name of the field. So you can say, give me a lens for the field bar, and it will give you, and it will inspect this type level list, compute that bar is the third element, and once it has done that, it will compute that bar is the second element, and once it has done that, it will generate lens that gives you access to the second element of this record. So it's like regular Haskell records, but really slow because they are represented as lists at runtime. So for every element in this list, you have a pointer in direction. You have the head of the list, then you have a pointer to its tail, where you have a pointer to the head and a pointer to the tail, and in the tail you have a pointer to the head and a pointer to the tail, and so on and so on. You have pointers and pointers and pointers, and referencing those pointers is kind of an expensive operation, while using regular record, you will have good performance because it's just a flat sequence of pointers, a pointer to the first element, a pointer to the second element, a pointer to the third element, and so on. But as long as the amount of elements is under, let's say, 100, it doesn't really matter. Or unless these records are used very heavily. But normally, it doesn't really matter if the representation is flat or nested, like with Vinyl, for code that doesn't have very hard performance requirements. So I wouldn't take that into account when designing some program component. If Vinyl gives you an elegant solution, don't worry about the performance unless you have hundreds of thousands of elements, or unless this data type is used a lot, really a lot in your application, and you need to get CPU cache hits. Same applies to union. If you need a sum of a couple of types, then you are probably going to be just fine with the union library that I have in package. But if you also need it to be super extra performant in some tight CPU loop, you want it to hit the cache constantly, then it's better to find another solution, which of which I cannot actually name a good one, because for flat tuples, we at least have them built into the compiler and provided via the base libraries. But for sums of n types, you are going to end up defining your own type each time. Well, actually, that doesn't sound too bad, defining new types. It's easy in Haskell. Anyway, more questions? Okay, I think this is it. Thanks to everyone for listening, and I can recommend trying Vinyl in your code if you find a use case for it, uh, and asking something in our Slack, because I like to talk about Vinyl. It's one of my favorite libraries. But also another thing that you will now have an easy time understanding is the amazing generics SOP library from Well-Typed, which is basically Union plus Vinyl used as a generics framework for Haskell. So we have our regular generics built into GHC, and they are cool, but they are not perfect. But the generics SOP library improves on them, giving you the same sort of inductive reasoning that I mentioned earlier. With Haskell generics, you with the built-in GHC generics, you are going to define a class for every operation on generics, and you don't have the validity checks of the type structures that you have, and you will also hit very inconvenient cases with generating generic representation as output with return type polymorphism. All of this is covered in their paper on generics SOP, but if you understand Union and if you understand Vinyl, then their paper will be very easy to read. So that's where I recommend you to what I recommend to read next, if this is interesting for you.